Hi, hello guys. Well, it's Teki. So again, maybe you are shocked that I've come for the second week in a row, but that's what we promised. Uh, Look, we're gonna postpone those springs for a while. We're gonna do them. At least you've got an idea of how to deal with springs. Actually, today we're gonna do concrete. Actually, concrete, in my view, it's more of a personal experience of what you have done when you were doing odd jobs here and there. Fortunately for me, uh, I was a youth during the time of uh, Nelson Mandela when he was the president. The comrade father leader, the president, introduced a project called Reconstruction and Development Program, where RDP houses actually were to be built for us, the poor, and so on. Now, I managed at least to work on those projects. I was an assistant actually. In so Tonta we say I was using a spade mixing cement with sand and stones and so on. Now, before those houses can be built, or before any permanent structure can be built, you need to build a foundation. But before building a foundation, you have to create a concrete, a hard rock, and so on. So to to manufacture or to establish a concrete, you need actually the cement. Why? In order to stick those materials together. That's the purpose of a cement. You need water as a facilitator, but water comes last. I think you need aggregates. By aggregates, I mean you need sand, which will be brought by trucks from rivers after it has been processed and found to be well. And then you need stones. I think stones in excess of I will say 4.7 or 4.7, yeah, 4.7 millimeters. They were actually used. We were actually mixing together. I personally mixed them together. It was a sand, I think three wheelbarrows with one bag of cement mixed together, and then we also put again three wheelbarrows of sand. So sand and stones are called aggregates. You mix them with cement to form concrete. Then you use water as a facilitator. Yeah, basically that's the case. And then we're to build what is so called strip concrete, not concrete rather, strip foundations. When you build houses, the foundations used for normal houses, yeah, I think it's strip foundations. And then there are the other ones where you have to use to build townhouses or skyscrapers. I think I can't remember what they call it, but that's not an issue. Now, that's the practical part. That's actually what we were doing at on the field, where maybe after mixing concrete and cast it, we built shutters around it. Normally, at the time, I think we were using planks, wood. Why? They were cheap, they were found everywhere. Sometimes they will only be those woods will be combined with I think what is speakers in English. I can't remember, but the speakers and Africans will use speakers to build shutters, and then we pour in concrete in there, and then we cast it. When it dries up, it forms a foundation. And then, yeah, basically that's the case. But before that, okay, I will mention that at a later stage. I don't think this is the part you would like to know, or you want to hear mainly. But the one that you want to hear is this. Actually, now the concrete, it is actually strong in compression, but it is weak in tensile. Because of that reason alone, that concrete is normally okay, we normally put what is so called reinforced steel bars to take tension in the high tensile area of concrete. Like say for instance, you're gonna see now we're gonna discuss reinforced concrete beams. So normally concrete in its normal form, it takes only 1/10 of its compressive strength in tensile. So that's why we put in the reinforced steel bars. Yeah, and then if normally there are two types, actually three, but I was told that only two normally is being used. We've got two types of reinforced concrete beams. We've got the economical beam, and then we've got an economical beam. And an economical beam, let's say for instance, this is our section. This, we did sections as well. You don't throw your language. This is the section, and then let's say for instance, let's build also what's so called the strain section, and then let's also form let's do also what is so called the stress section, just for an example. This thing, it goes like this, and then this is our section, and then we have installed what is so called reinforced steel bars from the top, maybe up to that point, and then this point here, normally they say at the bottom, they will say at the bottom of the reinforced steel is a cover. I would say normally at the center of the reinforced steel, but let's put it there at the bottom of reinforced steel. They will say it's a cover. Now this is, let's say this is the strain section. Let's say this is the concrete, this is the steel, and then let's say this part, this line, this horizontal line, we call it the neutral axis. This point there where the neutral axis cross this line is called the neutral axis. And then let's say we've got theta here and theta here. For obvious reasons, mathematically, this angle will be equal to that angle. Why? Vertically opposite angle. Another grade 3 nice maths there. Let's say, I think grade 5 maths. Vertically opposite angles. Now we will now this is taken place at the factory, at the design section, as to how to design a beam they're gonna use. Let's say for instance a lintel, that thing, Mr. Chester, on top of the window there, that thing is a beam. It's a reinforced concrete beam. It's just that it is not over designed. It is properly designed. If it is properly designed, nothing is too much than this. We call that an economical beam. But in a true sense, an economical beam is a beam where the stress, let's say this is the stress in the concrete, let's say this is the stress in the steel, where the stresses in the concrete and steel reach their safe maximum value at the same time or simultaneously, that beam is called an economical beam. And how do you see it? Normally both area of the steel and concrete are not known. The top part on top of this neutral axis, this part, the part on top of the neutral axis normally is concrete, and then the bottom part, this is where the steel work. The whole thing is concrete, but below the neutral axis This is where the steel take the tensile part, the tension. So now, let's say this part, the distance from here up to the line of neutral axis, we call it N. And then this is the width of the beam or breadth, doesn't matter. And then the distance from there, from the top up to the center of the reinforced steel bars here at the bottom, this distance there, it is denoted by the small d, and it is the effective depth of the reinforced concrete beam, reinforced effective depth. And then this one, the total length of the beam, or the total depth rather of the beam, it is denoted by big D, and it is the total depth of the beam. Yeah, basically this is the case. I think even in GCC I saw this, where they gave you a statement and you were requested to draw this. I think it was 2003 question paper, but that's not an issue. That's not an issue. For your information, this is N6. This is N6 information. Now, tan theta of concrete there, we said this line is called N. The distance from there up to the center, the neutral axis, is called N. And then we say tan theta is equals to tan theta of steel. The distance here, look. The distance from the neutral axis to the center of the beam, there, from the neutral axis, not there, to the center of the beam, we can just use a simple grade 4 mathematics. It will be this distance minus that distance. And what is that distance? It's N. So this distance will be what? The distance from here to there at the center of the reinforced beam. Obviously it will be small d minus N. It is that distance for obvious reasons. Now, tan theta here. Mathematics is simple. I think what do we call it? I think it's a simple grade 12 or grade 11 mathematics. It's a Mr. Chester, I think it's SOHCAHTOA, where you say sine is opposite over hypotenuse. In this case, tan is opposite over adjacent. It's a simple mathematics. It's just that we are using it now at a higher level of participation in terms of understanding. To participate in this, as I would like to put it, the way Mr. Orchestra put it earlier to someone, to participate in this, the basic knowledge of understanding from class is a minimum requirement. Otherwise, you won't understand. Just take this information here as a surplus. That's it. Now, tan is opposite over adjacent. What is opposite there is this, but what is adjacent is N. Is equals to what? Tan is opposite over adjacent is this, over what? The adjacent there is D minus N over D minus N. But remember, again, for your simple stress, strain, strength of material chapter, we all know that strain is equals to stress over Young modulus. Now, if this is the case, instead of strain here, we're going to substitute strain is equals to stress over Young modulus. Therefore, the stress of concrete over Young modulus of concrete multiplied by N is there. is equals to what? The strain or the steel strain is equals to what? It's stress there over E multiplied by what? Okay, let me use brackets to show that this, it goes as 1. D minus N is that distance from the center to there, is that distance. Right. Now let's be from this, let's do what is so called the stress ratio. The stress ratio is equal to what? Let's okay, this is difficult. Now let's do it step by step so that we shouldn't confuse each other. You see, there are people who are working and they can't get chances to go to classes, and they are using this this channel as a festival of ideas, so to speak. So please, if you attend, it might sound easy for you, but lucky, build a group and work together. Is equals to what? It's stress C multiplied by Young modulus D minus N. I've just cross multiply. Even this side I will do the same. Is the stress in the steel multiply by this Young modulus in the concrete multiply by N. Now let's see. It will be what? Let's say stress in the steel there. Actually, I'm making stress over steel and stress over concrete subject of the formula because I want a ratio. It is this I've divided by that already. I've divided by that, and then this side I'm gonna divide it by, okay, let's do it slow, step by step. Let me divide both sides by E C multiply by N, and then that side I divide by stress that. So this one is gonna cancel. I've multiplied by it. This one is gonna cancel. I've divided by it. I divided by this one and this one. So this one and this one, they have cancelled out. I'm left with what? This, which is the stress of steel over the stress of concrete. Is equals to what? Is equals to this one. Young modulus of steel over D minus N over young modulus of concrete. Let's make it, because someone will say it's steel. Young modulus of concrete multiply by N. Very, very, very important. They will tell you only for steel and concrete, the young modulus of steel over the young modulus of concrete is equals to M. And this M, they call it a modular ratio. And it is 14.96. But for simplicity, they will tell you that is equals to 15. And you're gonna see why now we say concrete, it's strong in compression but it's weak in tensile. Why? Because if you've got a certain amount of tensile stress, you can calculate how much compressive stress is there. Why? It will be that total number of stress that you have over the modular ratio, and it's equals to what? It will be the 10%. The number there, it will be 10% of the compressive stress in the concrete. That's a discussion for another, after a few minutes probably. But I think that Rochester gonna request another video. This is long, ne? I think you're gonna. But basically, this is what they want. This is equals to M. This is a modular ratio. Therefore, this ratio, stress over steel, is equals to this over this is M into D minus N over N. Why? This is equals to m, and they call it a modular ratio. This is the formula you're gonna use to calculate the position of the neutral axis in a reinforced in an economical reinforced concrete beam if the neutral axis is not given. I don't know, Mr. Chester, how much time you're gonna need, but let me push another for 2 minutes or 3 minutes on this one. This is the formula you're gonna use to calculate the position of the neutral axis. Now let's see. Normally we say the distance from here to the center of that there is a lever arm, is LA. The centroid of a triangle is what? It is this divided by 3. It is n over 3. Therefore what? Therefore the distance from here to the center of that triangle, it means LA, this one, LA is equals to d minus n over 3. This is the formula you're gonna use to calculate the distance between the force in the steel and the force in the concrete. Remember, these forces are equal. Why? Because the stresses in both the steel and concrete reach their safe maximum value at the same time. It's really, it should be like that. Now, yeah, and then this alphabets, D, small d, big D, N, LA they are so-called dimensions. But at the factory, I think they call them design factors of the beam, and you have to calculate them first if you are not given the position of neutral axis. I think we're gonna take an example on an economical beam before we do an uneconomical beam. But guys, look, I thought maybe we'll do that. Is why I said it's a lot of information. I think we'll do an economical beam. I think next time. It's just that this guy didn't understand the example he showed me, so I wanted to start first as to what's happened, because we don't want someone to cram the values. So like I said, normally this is more of a personal experience in practice. And then if this beam has to be deflected, they will tell you in books, they say it should be deflected by 1/360. But actually in practice, I later learned, I wasn't aware actually, so it's actually 20 millimeters. So we learn, man. We are the field students. We learn every day and so on. So yeah, we're gonna take a video, guys. I'm gonna see you in the next. I'm gonna see you now. This information actually goes with that example. Let me take that example, and then I'm gonna see you now. So there's no need to kiss you then for now. Okay, sharpura.